In this video, we'll be going through question 14 from the 2021 HSC Mathematics Extension 1 exam. This will be the fifth and final in a series of 5 videos covering the entire paper. So, part A. A plane needs to travel to a destination that is on a bearing of 63 degrees. The engine is set to fly at a constant 175 kilometers per hour. However, there is a wind from the south with a constant speed of 42 kilometers per hour. On what constant bearing, to the nearest degree, should the direction of the plane be set in order to reach the destination? Okay, so with a question like this, we definitely need to get some sort of diagram going. So the first thing we're going to do is we're going to place our starting point, our origin, and we have a destination that we're trying to get to, which is at a bearing of 63 degrees as a true bearing. Now, it's all well and good to have this diagram like this, but I think it's really important to put in a compass, a north, south, east, west, in order to essentially orient ourselves correctly, and often that becomes quite useful when we have to work out angles. So that's what I like to do, put it on my origin, and we can see that here we have our bearing of 63 degrees. So we've already added an angle onto this diagram. Now what we're told is that there is a wind from the south at 42 kilometers per hour. Now, if there's a wind from the south, that means it's coming from below, from south upwards in this sort of a direction. And so what that means is, if we want to land at point D, our plane, the pilot of the plane, is going to have to essentially undershoot. It's going to have to aim a little bit below D, something like this, and then the wind is going to push the plane up towards D. And so it's sort of like vector addition. We undershoot a little bit, and then the wind does its job and pushes us up towards D. So here in green, what we've got is we've got the path that the pilot should take in order for him to land at this point D after the wind has taken its effect or played its role. Okay, and of course the blue arrow here, that's indicating the effect of the wind. So we know that the wind is blowing with a speed of 42 kilometers per hour. And we also know that the engine is set at 175 kilometers per hour, a constant speed of 175, regardless of where it's aiming. Okay, now what do we want to find? We want to find the bearing that the pilot should fly at. In other words, we want to find the bearing of this path here in green. And what that means is we're really looking for this larger angle. Now, in order to find that larger angle, all I would really need to do is work out, well, what is this small angle in here? Theta, and then I can add that to 63, and I get my bearing that I want. Okay, so I've got a triangle. I've got two sides. I'm looking for an angle. Am I going to use the sine rule or the cosine rule? Well, I would need another side length in order to use the cosine rule. So that's obviously not going to happen. But in order to use the sine rule, I need another angle. And I can get another angle because these two lines here are parallel. Okay, they're parallel because they're both pointing vertically up in the north direction. And so what I've got is that this angle in here is equal to 63 degrees simply because they're alternate. So I'll add that in here. I'll say that this is 63 degrees. And might not be a bad idea to actually put this in your working out. Just call this point A or something. And then say angle ODA equals 63 degrees. And I will just say alternate angles as my reason. You're probably not going to be assessed on whether you're giving your reasons here because that's not in the syllabus anymore. But I mean, if you're able to identify what the reason is, you might as well add it. Great, so we've got 63 degree angle here, and now I can just apply my sine rule. Sine of this angle over the opposite side equals sine of this angle over the opposite side. So sine theta on 42 equals sine 63 on 175. So sine theta equals multiplying up 42 times sine 63 on 175. Putting this into the calculator, and here's a point that I just really want to make, especially just sort of about exam technique. This is an angle in degrees. Make sure your calculator is in degrees. often we're doing most of our stuff in radians, and so we forget to change it to degrees. So that's something you need to be a little bit cautious about. Putting that into the calculator, you get 0.213 ... And so our angle here for theta is going to be about 12.3 degrees. Okay, roughly 12.3 degrees. So our bearing, if we're looking for the bearing, that's going to be 63 plus that angle of theta. And so therefore, the bearing is, I would put this little step in, 63 plus 12.3. And I'm going to say that that's equal to 75 degrees to the nearest degree, because that's what they asked for. But because it's a bearing, I have to make sure that I give a 3-numbered answer. So this is 0.75, and also it's a true bearing, so I'm going to add a t at the end. And that's our final answer for part A. Part B. In a certain country, the population of deer was estimated in 1980 to be 150,000. The population growth is given by the logistic equation dp on dt equals 0.1p times c minus p all on c, where t is the number of years after 1980 and c is the carrying capacity. In the year 2000, the population of deer was estimated to be 600,000. Use the fact that c over p times c minus p is equal to 1 on p plus 1 on c minus p to show that the carrying capacity is approximately 1,130,000. All right, so we've been given this logistic equation, and we've also been given some conditions. We're told that in 1980, the population was 150,000, and in 2000, the population was 600,000. Now, t is being measured in the number of years after 1980. So that means that when t is equal to 0, which is at 1980, we have the condition that the population is 150,000, and in 2000, which is 20 years later, in other words, t equals 20, the population equals 600,000. So, I mean, in those 20 years, the population has multiplied by 4. All right, now what we want to do is we want to show, and I'm going to write here that we want to show c is 1,130,000 approximately, okay? And when we have to show something, that means that getting to the final result is not really that important. It's showing the steps that get to the final result. Just landing at this answer is not really important because they've given it to us. It's not really that special for us to come up with it. Okay, so we want to solve this logistic equation. It's separable. I'm going to bring everything with a p on one side and everything else, I'll keep it on the other side. Now, I am also aware of the fact that they've given us that c on p into c minus p can be broken down as these two fractions here. Okay, this is what we call a partial fraction decomposition. It's something you learn in Extension 2, but we don't even need to know it in order to do this question. It's been given to us. So I'm going to make sure that when I move all my p's to one side, I'm going to keep this c with them, because I can see that this is really this part of the fraction reciprocated. Okay, and I would like to keep that c there, even though it's not necessarily related to p. So I get c times dp over p into c minus p equals 0.1 dt. And now I've separated out my variables, I can go ahead and integrate both sides. Now on the left-hand side, I don't know how to integrate something like this using Extension 1 techniques, but I have been given this this fact here, this partial fraction decomposition, and so I can rewrite my integrand as those two fractions. So this is going to end up being the integral of 1 on p plus 1 on c minus p. And now those are two very easy integrals. They're just two-unit integrals, in fact. On the right-hand side, I can just integrate 0.1t. I'm not going to add a constant yet because I still have an integral here. Once I've lost all my integrals, then I'll add the constant. Okay, so this is going to end up being log of the absolute value of p. It's important to have absolute values. Actually, that should be minus log of c minus p equals 0.1t. Now I've got rid of all of my integrals. I can put one constant on either side. Doesn't matter which side. I'm just going to choose to put it over here, and I'm going to call it k. Obviously, I've used c for something else. So, and I'll say here where k is a constant. And we might even say that k could be any real number. Okay, let's try to unpack this a little bit. I've got log of, I can combine these two logs, p on c minus p equals 0.1t plus k. And now I'm going to exponentiate both sides to get the absolute value of p on c minus p equals e to the 0.1t plus k. Now this right-hand side, I can break it up as e to the k times e to the 0.1t. And this e to the k, I'm not gonna say anything else about it other than this. It is a constant, and we know that it always has to be positive because an exponential is always positive. Now what I'm gonna do is I'm gonna strip away these absolute value signs, and I'm gonna write p on c minus p, and in doing that, I have to add a plus or minus over here. So maybe I will write that e to the k, we knew that that had to be strictly greater than 0. And I'm saying strictly greater because I know it can't be equal to 0. But now if I have plus or minus e to the k, well that means by the positive case I can have all positive real numbers, and by the negative case I can have all negative real numbers. The only thing that I can't have is 0. And so what I'm going to do is I'm going to say that this is equal to a times e to the 0.1t, where a is any real number except a cannot be equal to 0. Okay, and we do have a way of writing that. Actually, if I just move this over here, the way that we can write this is by saying all of the real numbers, and we want to cut out anything that comes after. So the thing that comes after is just the set with the number 0 in it. Anyway, the point is that this a is a constant, any constant except for 0. Cool. So I've got p on c minus p is equal to this. Now I want to start subbing in my conditions, because what I've really got here is two unknowns. There's an a and a c, and I've got two equations here that'll give me, or two initial conditions that'll give me two equations. And from those two equations, I can solve simultaneously and work out the a and the c. Now I actually don't even care what a is. Remember, all I'm trying to do is show that c was equal to 1,130,000. So I'm going to start by subbing in when t is equal to 0. I know that my population is 150,000. And I'm going to call that equation 1. And I do the same thing with t equal to 20. And I call that equation 2. Now I've got two equations. I can substitute in equation 1 into equation 2. That means I'm replacing the a here with this expression. So I'm going to say sub 1 into 2. And let's see what we get. Okay, we get to this point here. And now what we're trying to do is we're trying to solve for c. And remember, it's not like we don't want to skip any steps. We know that this needs to be the answer. We want to show the steps that are required in order to get to that answer. So the first thing I'm going to do is, well, I want c to be made the subject. I'm going to flip both sides of this equation. I'm going to take reciprocals. Okay, so I've taken reciprocals here. One thing I can notice actually is that, and I might just do it now to save myself rewriting it, is that if I multiplied both sides by 600,000, this would obviously disappear. This would cancel and give me a 4 in the numerator. So what we're basically doing now is multiplying both sides by 600,000, and we get something like this. Okay, so now what I'm going to do is I'm going to expand out these brackets here. I'll get 4 e to the negative 2c minus 600,000 e to the negative 2, and that's equal to c minus 600,000. Now I'll bring that c over to the other side, and I'll get c, factor it out, 1 minus 4 e to the negative 2, and I'll bring the 600,000 over to the right-hand side, and at the same time I might as well factor that out, 1 minus e to the negative 2. c would become this divided by this. And now at this point I've shown all of my steps. the final thing that's remaining is for me to simply punch this into a calculator. And when we do, we get 131,121.335. And this is approximately, well, let's say this is approximately equal to 1,130,000 as required. Okay, and so we've shown what we wanted to show, making sure that we've put in the necessary steps. And that's the end of part B. Part C now. The first part says, for vector v, show that v dot v equals the length of v squared. So this is a 1 marker. It's relatively simple. It's pretty much a free mark coming towards the end of the exam. So you take these when you can get them. Now, we want to prove this. Now, obviously, many of us know this as a fact, but we want to prove it. And the way it's proven, there's a couple of ways, but probably the simplest would be to let the vector v be x, y, and then just compute both sides and show that they're equal. So the left-hand side is equal to v dot v, which is xy dot xy. And of course, when you take a dot product, you multiply component-wise. So this is x times x, which is x squared, plus y times y, which is y squared. And then the right-hand side, that's going to be the length of v squared, which is the length of the vector xy squared, which is the square root of x squared plus y squared, all squared, which is x squared plus y squared, and that is the same as the left-hand side. And so therefore, v dot v is equal to the length of v squared. Okay, and there's your 1 mark. Now part 2 says, in the trapezium ABCD, BC is parallel to AD, and the length of AC equals the length of BD. Let A be equal to AB, B be equal to BC, and AD be equal to K times BC, where K is greater than 0. Using part I or otherwise, show that 2A dot B plus 1 minus K length of B squared equals 0. Okay, so we've been given some labels for certain vectors. I'm going to add them in on the diagram. So AB, we have called this lowercase a. This vector BC is called lowercase b. And we're also told that the length, or that the vector AD rather, is equal to K times the vector BC. In other words, it's K times lowercase b. So I can add this in as well. This is K times lowercase b. All right, and then we're told that these two lengths are the same. The length of these two vectors are the same. So here they are, AC and BD. Now what we want to do is we want to show this, and it gives us a hint. It says using part I. Now it does say or otherwise, so we don't necessarily have to use part I. But since it says using part I, you probably want to use that result that you proved, which is that the length of a vector squared is equal to the vector dotted with itself. Now the only thing that I have at the moment that's got anything to do with lengths is this given condition here. So what I'm going to do is I'm going to start off with this. These two lengths are equal, and then if their lengths are equal, then the square of their lengths should also be equal. So I can square this, and I get the following. But the reason that I want to square it is because now I'm able to introduce that result that we had previously from part I. So I can take the dot product of each of these vectors with itself. And now what I've done is I've introduced a dot product into what I've got. And I know that that's a good idea because eventually I want to get a dot product, right? I can see there's an A dot B here. So the question is, how do I now introduce A's and B's? Well, for each of these vectors, A, C, and B, D, I can write them in terms of A and B. So this vector AC is simply going from A to B and then from B to C. So this is A plus B. So I can write this as A plus B dotted with itself. And then for BD, well, how do I get from B to D? I go in the opposite direction of A. So this would be negative A plus KB. So here I've got negative A plus KB dotted with itself. Whoops, that K shouldn't be a vector. Okay, now what I want to do is I want to expand this out, expand out the dot products, and then see what I can do to simplify. So I'll get A dot A plus A dot B plus B dot A plus B dot B. And that's equal to negative A dot negative A. That's going to give me A dot A, because the two negatives will cancel to give me a positive. And then I've got minus A dot KB. Then I've got minus KB dot A. And then finally I've got K squared B dot B. Okay, I've basically done KB dot KB. I've taken the K out as a common factor. That scalar really does just move in and out of the dot product as it pleases. I tried to leave it here and here, but we can move it in and out of the dot product. Now, what can we simplify? Well, I can see there's an A dot A on this side and an A dot A on that side, so those will cancel. And then we know that the dot product is commutative, which means that the order in which I take a dot product doesn't matter. So I've got A dot B plus B dot A. That's going to be 2 A dot B. Here I've got a B dot B, and I know that a vector dotted with itself is the length of the vector squared, so that's the length of B squared. And then what about here? I've got negative A dot KB. Now we already just said that we can move the K in and out of the dot product, so this is negative K A dot B, and this is negative K A dot B as well, so I've got negative 2K A dot B. And then I've got K squared B dot B, but K squared B dot B is the same as K squared, the length of B squared. Now let's move everything over to the left-hand side and see what we can get. All right, so we've moved everything to the left-hand side, and now I want to see what I can factorize. Well, I can factor in a 2 A dot B out of this, and I get 2, 1 plus K A dot B. And then here I've got a length of B squared that I can factor, and I'm left with 1 minus K squared, the length of B squared. Okay, I'm almost at what I want to get to. I can see that this is what I want to get. But what we can do is we can factor this as a difference of two squares. And we get 2 times 1 plus K into A dot B plus 1 minus K, 1 plus K, the length of B squared, equal to 0. And now I'm able to cancel off this 1 plus K with that 1 plus K. I'm basically dividing through by 1 plus K. And I'll be left with 2 A dot B plus 1 minus K, the length of B squared. Now I should justify, or I should say equal to 0, but I should justify why I've been able to do this. Why have I been able to divide by 1 plus K? Well, that's because I know K is greater than 1. Oh, not greater than 1, I think it said greater than 0 in the question, but that means that 1 plus K is greater than 1, and in particular, that means that 1 plus K cannot be equal to 0. So it was safe for me to divide by that factor of 1 plus K because it's not equal to 0. Okay, and so we've ended up at what we wanted to prove, and I suppose we can say as required to end off. And that's the end of part C. Part D. At a certain factory, the population of faulty items produced by a machine is P equal to 3 on 500, which is considered to be acceptable. To confirm that the machine is working to this standard, a sample size n is taken, and the sample proportion p hat is calculated. It is assumed that p hat is approximately normally distributed, with a mean of p and a standard deviation, or a variance rather, of p times 1 minus p on n. So they've been nice to give us those formulas. Production by this machine will be shut down if p hat is greater than or equal to 4 on 500. The sample size is to be chosen so that the chance of shutting down the machine unnecessarily is less than 2.5%. Find the approximate sample size required, giving your answer to the nearest 1,000. Okay, so there's lots of words going on here. We have to try to unpack the scenario. We have P being given to us as 3 on 500, and that's going to be really useful. And what else are we told? We're told that the machine will shut down, or the production by this machine will shut down if p hat is greater than or equal to 4 on 500. So the probability of this machine shutting down, or this production shutting down, is equal to the probability that p hat is greater than or equal to 4 on 500. And what we want to do is we want to find the sample size n. Basically, n is what we're looking for here. We want to find the sample size such that this probability is less than or equal to 2.5%. Okay, so we want this probability to be less than 2.5%. All right, now we're told that p hat is approximately normally distributed. So I can say that p hat is normally distributed with a mean of p and a variance of p into 1 minus p on n. Okay, so if I want to, I can write down, I can write it like this. P is 3 on 500. And then we've got 3 on 500 times, well, I suppose this is going to be 497 on 500 all over n. Okay, sometimes I like to write down my variable in this way, if it's normally distributed or if it's binomially distributed or whatever, because then it allows me to see exactly what my mean is and what my variance is. Okay, but we want to basically find n from this condition here. This is the condition that we're looking for. We want our probability to be less than or equal to 2.5%. Now what I'm going to do is I'm going to have to standardize this. Remember, this is a normally distributed random variable, but I'm going to standardize this so I can work with z-scores. So let's go ahead and do that. So p, I have to subtract off the mean. The mean is p, and I divide by the standard deviation sigma. And that needs to be greater than or equal to 4 on 500 minus p over the standard deviation. And we want this to be less than, this probability to be less than 2.5%. Okay, now let's actually go ahead and substitute in the value of p here and the value of sigma. Actually, the value of sigma, I'm going to leave it because it's a little bit ugly. But I will sub in p because p is 3 on 500. So I have 4 on 500 minus 3 on 500. Well, that's easy enough to simplify. This here has now been standardized. So this now is simply z. But this now becomes 1 on 500 all on sigma. So this is 1 on 500 sigma. And we want this to be less than 2.5%. Okay, so here we've got a z-score. And we're trying to find the condition so that this probability is less than 2.5%. Now the number 2.5% hopefully is one that you're familiar with, okay? And if you're not familiar with it, let me show you why it's one that you should be familiar with. What I'm going to do is I'm going to quickly draw up a normal distribution curve, and we're going to analyze some of the areas underneath the curve. Okay, so here we have our normal distribution curve, and what I've drawn out are the standard deviations of 1, 2, and 3, basically the z-scores going up and down at standard deviations from the mean. Now, this number 2.5 is one that I would recommend. I very rarely recommend memorizing things, but this is probably something that I would recommend memorizing, or at least being familiar with. This number is associated with the empirical rule that is related to the z-score of 2, okay? Because the empirical rule for 2 tells us that in between -2 and 2, we have 95% of this area is covered in here. So what that means is that the remaining 5% exists outside greater than 2 and less than -2. Now, because this is symmetrical, this area here is the exact same as that area there. And so if I only want to work out what one of them is, well, that would be half of 5%. So that tells me that this area here, which I'm now shading in green, that area is half of 5, which is 2.5%. And so what I'm looking to do is I'm looking for a z-score which is greater than some certain value, and I want that to give me a probability less than 2.5%. Now, if I was at 2, if my z-score was 2, then I have z greater than 2. So for example, something like this, let me do it in pink. Then here, this is the area that I would be looking for. And that area is obviously less than 2.5% because I've still got this little bit of green sitting in there. So what I really want is I want this value, 1 on 500 sigma, I want that to be equal to 2. Because then when z is greater than 2, then my probability will be less than 2.5%, which is the condition that I want. So essentially, I want to now solve 1 on 500 sigma is equal to 2. Okay, let's make sigma the subject. Sigma would be 1 on 1000. And I'm actually just going to square both sides here because I know that I need to square eventually because up here, this is our value of sigma squared. So now I can substitute that in. I get 3 on 500 times 497 on 500, all divided by n is equal to 1 on 1000 squared. Now I need to make n the subject, so I'm going to multiply up. N is going to be 1000 squared times 3 on 500 times 497 on 500. Now I just do want to go back really quickly for 1 second and write here that I should probably justify this step saying by the empirical rule. Okay, so I'm going to say by empirical rule here to sort of, because I mean this could be just a bit of a random jump. You should really try to justify that. The rule here is, the reason is the empirical rule. Anyway, continuing on, this is now something that I would punch into my calculator and see what I get. When you type it in, you get 5964, and it says we want to find n, the sample size, to the nearest 1000, and so this is equal to 6000. And I'll put in brackets here to the nearest 1000. Okay, so this is a nice question. It also links back to our 2-unit knowledge, our advanced knowledge, talking about the empirical rule, and it's really pretty tough to do unless you can notice that 2.5 is a number that's associated with the empirical rule. Typically the numbers that we remember are 68, 95, and 99.7, but for each of those, there are some numbers that are associated with them. For example, here we have 2.5 is associated, but also 5 is associated with the empirical rule for a z-score of 2, because that's the stuff outside. And so those numbers are numbers that you need to be familiar with when you're dealing with this statistics topic. Part E. The polynomial g of x equals x cubed plus 4x minus 2 passes through the point 1, 3. Find the gradient of the tangent to f of x, which is equal to x times the inverse of g, at the point where x equals 3. Okay, so this is the information we're given. We have some g of x as a polynomial x cubed plus 4x squared minus 2. It passes through the point 1, 3. And then we want to find the gradient of the tangent of this function when x is equal to 3. Now, one thing you might try to do is, well, you recognize that you have g inverse here, and so you might try to work out what g inverse is. But it's actually very difficult to do, because when you set this equal to y, and then swap your x and y's and try to rearrange to make y the subject, it's very difficult to do because you have an x cubed here. If it was an x squared, it's doable, but with the x cubed, makes it quite difficult. So that's not the approach that we're going to go for here. We have to do something else. Now, what are we going to do? Well, let's suppose we have no other idea what to do. We know that we want to find the gradient of the tangent of this function. So that means we're going to have to differentiate f. We need to find f dash. So let's go ahead and use the product rule here and see what we get. So f dash, it's a product of two functions. So I'm going to differentiate the first and then leave the second. So it'll be 1 times g inverse plus, now I leave the first and I differentiate the second. X times the derivative of g inverse. But I don't know what g inverse is, so I can't directly differentiate it. There has to be some other way that I'm going to do this. And this is how we deal with this sort of an issue, the derivative of the inverse. It's a very subtle dot point in the syllabus, but as you can see, it has been assessed. And this is a trend in the HSC, in these newer HSCs of the new syllabus, assessing small areas of, or dot points which are, often glanced over. So to differentiate this, what we're going to do is we're going to recognize that if I take g and compose it with g inverse, what we get is the identity. So I suppose what I should do in my working out is I should say now g of g inverse is equal to x, because this is not really following directly on from the previous line. Writing the word now kind of indicates to the reader that I'm starting something slightly new. But what I want to do is I want to differentiate this, and let's see what we get. Don't be intimidated by the notation here. Really what we have is a function. Within it is another function. So we're going to have to use the chain rule to differentiate this. So that'll be g dash of g inverse. And then we have to multiply by the inside derivative. Well, the inside derivative is d dx of g inverse. And that's going to have to be equal to the derivative of the right-hand side, or the derivative of x is just 1. And so if I want to get this by itself, the derivative of the inverse, all I have to do is divide by g dash of g inverse. So therefore, d on dx of g inverse of x equals 1 over g dash g inverse of x. Okay, great. Now I can substitute this back up into this expression for f dash. So I can say, therefore, f dash of x is equal to g inverse plus x multiplied by this, so x times 1 in the numerator, divided by g dash of g inverse. Okay, now we want the gradient at x equals 3. So we want to evaluate f dash of 3. Okay, so f dash 3, that's going to be equal to g inverse of 3 plus 3 over g dash of g inverse of 3. Now, how do I know what g inverse of 3 is? I don't have an equation for g inverse in order to plug 3 in. But what I do know is I know that g passes through the point 1, 3. Now, another way of saying that is that g of 1 is equal to 3. And I know that when I take the inverse, the role of x and y swap. So this means then that g inverse of 3, which is now playing the x role, is equal to 1, which is now playing the y role. So this here is my x and this is my y. And so I know what g inverse of 3 is. It's equal to 1. So I can now say that this is equal to 1 plus 3 over g dash of 1. And I'll say since g inverse of 3 equals 1. Okay, now all that's left for me to do is to evaluate g dash at 1. But I can do that because I have g, I can differentiate it and then sub 1 into that. That's not an issue. So on this, I suppose just continuing on, I can say now g of x is x cubed plus 4x minus 2. So g dash equals 3x squared plus 4. G dash of 1 is equal to 3 plus 4, which is 7. And so now I can sub this 7 in for g dash 1. And I can say, therefore, f dash of 3 equals 1 plus 3 on 7, which is 10 on 7. And that is my final answer. So I might make a final statement. The gradient of the tangent at x equals 3 is 10 on 7. Okay, and that is the end of that question and the end of the paper.